Hello everyone, welcome to my channel Essentials of Electronics. In today's video, we are going to discuss two important things. Some examples of binary weighted resistor. Yes, binary weighted resistor DAC. In my previous video, I have given the operation and I have solved one example of binary weighted resistor DAC. So few more examples of binary weighted resistor DAC will solve, and another type of R to 2R ladder DAC. This is the topic today. We'll move into example. Example number 1 for binary weighted DAC. So 5-bit binary weighted DAC is given in, yes, assuming the input voltage at each bit is either 0 volts or plus 5 volts. For logic 0 and 1 respectively. Yes, this is the thing. We have to calculate the step size or resolution, full scale output voltage, V out for the binary code 11010 and binary input for V out. So these are the questions we will be solving now, and the given data is RF is equal to 10 kilo ohm, R4 is the MSB 25 kilo ohm. This is the data given. We'll try to solve it. So for this, we have to find step size. So from the question, it is understood that it is a 5-bit binary weighted DAC. The step size is equal to minus 5 RF divided by R naught. Okay. So R3 is equal to 50 kilo ohm. R2 is equal to 100 kilo ohm. So these are the values, isn't it? R1 is equal to 200 kilo ohm. So in a binary weighted rack, the values of the resistors increases. Since the values of the resistors increases, the current also shows variations. R0 is the LSB. Therefore, the step size is equal to minus 5 RF divided by R0 is equal to minus 5 into 10 divided by 400. 10 kilo ohm divided by 400 kilo ohm will give you minus 0.125 volts. Okay. Second question that was asked was, second part of the question is calculate the full scale output voltage. The data that was given is 1111. Yes. For this data, we need to calculate V out Fs, that is full scale. So the full scale output voltage V out Fs is equal to 2 power 5 minus 1 into step size, which is equal to 2 power 5 minus 1 is 31 into minus 0. Step size is 31 into minus 0.125 volts is minus 3.875 volts. So this is the value of the full scale value of the output voltage. And for data input, the third part of the question was for data input 11010, we need to calculate the output voltage. So the output voltage V0 is equal to 11010 into step size. So 11010 will give us Is that 26? So it is 26 into step size value is minus 0.125 volts. So with the output voltage for the given binary values minus 3.25 volts. The fourth part of the question is we need to calculate the binary input having V out divided by step size is equal to minus 0.75 divided by minus 0.125, which is equal to 6 base 10 is equal to 00110 base 2. Yes, so these are the different sections. So we calculated for the given question, we calculated the step size, full scale output voltage. For a given data of 11010, we calculated the output voltage and the binary input was asked for 0.75 volts. So we have calculated it. Yes, we are now moving into another example. The second example is the analog output of a 5-bit DAC is connected to a light emitting diode through an unity gain buffer so that its voltage is used to light up the LED. So I'll show it with a simple block diagram. So 5-bit DAC, as per the given question, a 5-bit DAC is connected to an inverting buffer which is used for lighting an LED. LED is the output. So on the 5-bit DAC, 1, 2, 3, 4, 5. 5-bit DAC, a digital input is given to a 5-bit DAC, a binary weighted DAC, and the output of this will be an analog. This analog signal is fed to an LED output through a buffer. So for this, given that RA is the LSB resistor, least weighted resistor of the DAC, having a value of 800 kilo ohm. So the least bit LSB has 800 kilo ohm. Then we can write down the resistance values of all the DAC input resistors. What are the others? We can write the values RB, RC, RD, and RE ourselves, isn't it? Given that the magnitude of the full scale output of the DAC, the second part, this is the first part of the question. Second part of the question is we have to find the given that the magnitude of the full scale output of a DAC, V output is given as minus 3.875 volts. Calculate the value of the feedback resistor. Assume that a logic 1 at the inputs of the DAC is plus 5 volts and logic 0 is 0 volt. Then the third part of the question is if the LED requires at least an output voltage of minus 1.5 volts to turn on and that it can withstand a forward voltage EFL minus 15 volts. Determine the range of input binary codes to the DAC that are able to turn on the LED. So multiple questions are given. This question is an application oriented question. So we need to find out the answers for all this. The first part of the question, this is the block diagram of the question. The first part of the question is RA is given. We need to find the values of other resistors. Then output voltage is given. We need to find out the input. And for an output voltage of minus 1.5 and the forward voltage for the LED is given. For this, we need to find out the binary codes for their turn on and turn off. So we'll try to solve it, find the solution for all the three parts of the question. So what was given? RA was given. RA is equal to 800 kilo ohm. We are supposed to find the other parameters. RB is equal to RA divided by 2, which is equal to 400 kilo ohm. RC is equal to RB divided by 2, or RA divided by 4, which is equal to 200 kilo ohm. RD is equal to RC by 2 or RA by 8 is equal to 100 kilo ohm. RE is equal to RD by 2, or it is RA by 16, which is equal to 50 kilo ohms. So this is the way we need to calculate the other value of resistor. So what do you understand from this is RA is 800 kilo ohm, 400 kilo ohm, 200 kilo ohm, 100 kilo ohm, and 50 kilo ohms of RV, RC, RD, RE respectively. So as the values of resistors are varying, we see that one end of the resistor is 50 kilo ohm and the least significant bit value is 800 kilo ohm. The values of the resistors are varying, and hence the currents passing through this is also varying. This is one of the drawback of binary weighted resistors. Okay, we'll move into the solution of the second part of the circuit. The question was the full scale value of voltage is minus 3.875 volts. We need to find R value. So step size is equal to minus 3.875 divided by 2 power 5 minus 1 is equal to minus 0.125 volts. So the step size is also given by, we have another formula, minus 5 RF by RA, which is also equal to minus 0.125 volts. Yes. Next, we'll move on to the third part of the question. Yes. The output voltage that was given minus 1.5 volts, and we need to find the binary. The equivalent binary for this is equal to minus 1.5 divided by step size, which is equal to minus 1.5 divided by 0.125 is equal to 12. 12 or 12 base 10. This is 0.1100 base 2. Yes. Now using this data, the question was given the forward voltage was given, and the forward voltage for making the LED glow was 15 volts. Yes. So we'll have to try to know the codes for turning on the LEDs. I continue this problem here. If minus 15 volts exceeds the full scale output of minus 3.875 volts, then the input code should turn the LED on are 12 to 31, or this is 12 to 31 base 10, isn't it? So it is 0.1100 base 2 to. So this is the solution of the binary code that is required to turn on the LED. So the advantages of binary weighted resistors are simple construction in analysis and fast conversion. But the disadvantage of binary weighted resistors are it requires large range of resistors. 2000:1 for 12-bit DAC with necessary high precision for low resistors, and it requires low switch resistance in transistors can be expensive, therefore usually limited to 8-bit resolution. As the bit goes on increasing, the ratio of the resistors are 2000 is to 1, and hence unequal values of current flows in the circuit, which in turn itself causes a big drawback in the precision of the binary weighted resistor. So to avoid this, the other resistor that was modified from binary weighted resistor is R to 2R ladder resistor. In this, equal values of resistors were framed and equal values of currents were fed in. So R is from this. Why the name R to 2R? What I am now drawing is 4-bit R to 2R ladder. An op amp here with an RF. Yes, we have switches here. We have switches here to be connected. So these values are 2R. Since the arrangement is that of a ladder, it is called R to 2R, R to 2R, R to 2R, R to 2R, and R to 2R. So we have 4 pairs of R to 2R. The diagram shown here is a 4-bit DAC. What is the operation of this? Here the inputs, these are switches, 4 switches, S1, S2, S3 for example, S4. If the switch is connected to the op amp, then the digital data is 1. Digital input is 1. If the switch of the 2R resistor is connected to ground, then it is 0. So if the digital switch is connected to the op amp, then the digital input is 1. If the switch uh, to connected to 2R resistors, S1, S2, S3, S4 is connected to the ground, then the digital input is 0. So by modifying the binary weighted resistor tag, a proper configuration of the R to 2R ladder network proves that the high resolution is obtained and unequal values of resistor leading to avoidance of bulky resistors are avoided in this kind of R to 2R ladder network. So the equivalent value of resistor R equivalent is equal to 2R into 2R divided by 2R plus 2R. So the equivalent values of this can be determined. V3 is equal to 1 by 8 times of V reference. V2 is equal to 1 by 4 times of V reference. And V1 is equal to 1 by 2 times of V reference. Therefore, the output voltage V0 is equal to minus R into the bit V reference divided by 2R into bit 3 plus V reference divided by 4R into the second bit plus V reference divided by 8R into the first bit plus V reference divided by 16R into bit 0. B3 corresponds to bit 3, B2 to bit 2, B1 to bit 1, and B0 to bit 0. So this is the final expression of the output voltage of an 4-bit ladder DAC. So according to the bit, the equation can also be modified. Therefore, V out is equal to minus V reference into B3 by 2 plus B2 by 4 plus B1 by 8 plus B0 by 16. For general n bit 2R ladder, we can write the output expression as V output is equal to minus V reference sigma I is equal to 1 to n B n minus I to 1 to the power of I. This is the expression of R to 2R ladder network. He will try to solve one problem. So in a R to 2R ladder network, a 3-bit, for an example of 3-bit, if the reference voltage V reference is equal to 1, and if all the switches are connected, the output current can be calculated. Well, these kind of resistors, R1 is equal to 2 kilo ohm, R2 is equal to 4 kilo ohm, and R3 is equal to 8 kilo ohm. I0 is equal to total current is equal to I1 plus I2 plus I3, which is equal to V reference by R1 plus V reference by R2 plus V reference by R3, which is equal to V reference by 1 kilo ohm into 1 by 2 plus 1 by 4 plus 1 by 8. Therefore, the output voltage V0 is equal to minus I total into RF, which is equal to minus 1 kilo ohm into 0.875 milliamps is equal to minus 0.875 volts. This is the output voltage for the given value of 3-bit DAC R to 2R. So the advantages of this is only two resistor values R and 2R will be involving in the circuit, does not require high precision resistors. The disadvantage for this is compared to binary weighted, the lower conversion speed is there in R to 2R ladder network, but comparing to the weightage of the resistors, R to 2R ladder network shows high precision and more advantages than binary weighted resistor DAC. So in this video, we have discussed the examples of binary weighted rack and R to 2R ladder DAC, and an example was solved in calculation of digital input to output voltage. Thank you.